So continuing on 9.1, calcium. Calcium is an important thing to have in your diet. Calcium is a vital nutrient for healthy bones and teeth. The National Institute of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers aren't getting enough calcium. Is this true? We're going to perform a significance test to find out. First thing we need to do is state the hypotheses for this significance test. We should be able to do this by now, based on yesterday's amazing amount of information that we learned. What do you guys think the null hypothesis is for this problem? What is 1,300? The mean. If I'm talking about the mean of a population, that would be what notation? Mu. So, mu equals 1,300. That's what it's supposed to be. But the NIH is concerned that teenagers aren't getting enough. What is the alternative hypothesis? That mu is less than 1,300. Oh, I forgot the milligrams. My bad. All right, and again, we need to define our parameter. Mu is the true mean calcium intake for teens. All right, so that's our null and alternative hypothesis. The null hypothesis is that teens are getting what they're supposed to, but the suspicion or the concern is that they're getting, in fact, less than they are supposed to. And so we're going to do this significance test. We're going to take a sample, and we're going to see what is going on here. All right?
What's up?
Do you have any questions about the null and alternative hypothesis? You feel good about this? Cool? Okay. So, the NIH takes a random sample of 20 teens and records their food and drink consumption for one day. The researchers then compute the calcium intake for each student. Data analysis reveals that the sample mean is 1198 with a standard deviation of 411. Okay, time out. Based on that sample, are the teens getting less than 1,300 milligrams of calcium? Obviously, 1198 is less than 1,300, is it not? Okay. All right, 1198 is less than 1,300, so it seems like we should just be done, right? But no, here's the problem. Is this difference due to sampling variability, or is it actually so low of a sample, as extreme or more extreme? Is this so low of a sample that there's no way it could be sampling variability and there really is a problem going on? So we do the significance test and we get a p-value of 0.1404. Here's what that p-value means. Assuming the true mean is 1,300 milligrams of calcium, there is a 0.1404 chance. By the way, you guys know that that's 14% basically. Yeah, hopefully. All right. There is a 0.1404 chance of getting a sample as extreme or more extreme than the one we observed. So basically, guys, here's what we've got. We've got a normal distribution. I know it's normal because they're all normal. 1,300 is our mean. We took a sample and we got 1198. The probability that we get a sample that is as extreme or more extreme than that is 0.1404. That is the chance that we have gotten this sample due to sampling variability. Is that low enough that you think that teens really aren't getting the 1300? Is this too low for you to feel comfortable that this was not just sampling variability? Or do you think that this was just sampling variability? So there's a 14% chance that we get a number that is this low or lower on an actual 1300 milligram distribution. So how low, or do you think that that's too low? It depends. How low is too low? Well, we have to have something to compare it to. But for now, that is the p-value, okay? All right. And what do we compare that p-value to? We compare it to the statistical significance level. Whoops. I apologize. The final step in performing a significance test is to make a conclusion about the competing claims that we're testing. It's either going to be that the null hypothesis is the one that we're going to settle on and say, well, we don't have enough evidence to prove anything else, so we got to just go with what they say. Or do we have evidence that there really was a difference and it wasn't just sampling variability? So we're going to make one of two decisions based on the p-value. We are either going to reject the null hypothesis, or we're going to fail to reject the null hypothesis. Well, that seems weird, doesn't it? So here's the deal. You guys know about trials. I'm sure everyone's seen a movie where there was a trial at some point. When the person that's on trial, they are innocent until proven guilty, right? They have the trial, and the jury goes back, bless you, and deliberates. When they come back, what are the only two decisions that they could have given? That the person is either what or what? Guilty or not guilty. Why does the jury never come back to say, we have found this person to be innocent? Why not? Why don't they say that?
Because you're always innocent. You're innocent until proven guilty.
You're innocent until proven guilty. So the whole trial is trying to do what? It's trying to prove the person's guilty. Now, the defense is like, no, they're not guilty, I promise. This evidence that you're seeing, it's really not true. Okay, not true, okay. So, we're trying to prove that they're guilty. The jury has to make a decision based on the evidence.
What are you looking at?
You have gotten up 14 times today already.
I have to throw this away. What?
All right. The jury has to look at the evidence and say, we have enough evidence to believe beyond a shadow of a doubt that they are guilty. Or they look at the evidence and say, we have some evidence here that kind of looks like something was a little weird, but we don't have enough evidence to feel good enough to send them to jail. So we're going to say that we don't think they're guilty because we don't have enough evidence of that. That's what we're doing here, okay? The null hypothesis is true unless we can prove otherwise. We are always trying to prove the alternative. We can either reject the null hypothesis because we got enough evidence to prove the alternative. Huh?
Call it its real name.
Or we can fail to reject the null hypothesis because we didn't get enough evidence to show the alternative. Okay? But here's what we never do. Just like a jury, we never come back and say that the null hypothesis is for sure true, because we don't really know that. So you are going to never, ever, ever accept the null hypothesis. Okay? So, let's just say what's going on here. Basically, you guys, we have a hoe. And the hoe is on trial. And we're either going to reject that hoe, or we're not going to be able to reject the hoe. But we're never going to accept the hoe. Okay? Never. We don't ever accept hoes. Don't do it. Don't do it. You either have enough evidence to prove that they're really not a hoe. Ha! The alternative, right? Ha! Right? Ha! They're not a hoe. Okay, so you can reject the null hypothesis. Ha! Or you don't have enough to reject the null hypothesis, but you never, never, never accept the hoe. Okay? How do you know which one to do? It is fully based on the p-value. If the p-value is less than alpha. What is alpha? Alpha is the significance level. Alpha is the significance level. It's basically your decision point. If your p-value is lower than your alpha level, your significance level, then you're going to reject the null hypothesis. If your p-value is greater than or equal to your alpha level, then you have to fail to reject the null hypothesis. That does not mean you're accepting the null hypothesis. You're just not able to reject it. You didn't get enough evidence. Your evidence wasn't good enough. Okay? All right, so my first year teaching stats, I went to a conference where they taught teachers how to teach stats. And my teacher was a 70-year-old woman named Peggy Smeltzer. Sounds 70, right? And she was teaching us about p-values and about how to make a decision on a significance test. And she said to a class full of educators, if the p-value is low, you reject that hoe. And we were like, excuse me, ma'am, what? Huh? She told us that that is the best way to remember when you are going to reject the null hypothesis or not. If the p-value is low, lower than the significance level, that's when you get to reject the hoe, the null hypothesis. Okay? So, what are we going to do when our p-value is low?
Reject the hoe.
We're going to reject that hoe. That's right. That's absolutely right. Yes, 100%. If the p-value is not lower than the alpha, then you're going to fail to reject. But Hayden, what are you never going to do?
Never accept no hoe.
That's right. You're never going to accept a hoe.
That's right.
That's right. This is more than statistics, you guys. This is a life lesson. All right, cool. Here we go.
Base, beta middle.
Oh my.
This Lakey's so Sigma.
Yes.
Sigma Andrew Tate, Miss Lakey.
I will. I need to update Canvas today. All right, so let's look at this in terms of an actual example, an actual problem. I forgot to update the name in this problem, but we'll pay homage to our Officer Trainum here. So, Officer Trainum, or whatever SRO at the time, wants to determine if it is worth the cost to install a speed sensor wants to see if it is worth the cost to install a speed sensor and traffic camera at the entrance to McKinney Boyd High School on Lake Forest. Do you guys think there's some speeding happening over there? No, never. McKinney PD will install the speed sensor if and the traffic camera if they are convinced that more than 20% of the cars are speeding in the school zone. Officer Trainum selects a random sample of 100 cars in the school zone, measures their speed, and finds that 28 of the 100 cars are in fact speeding. Time out. You guys, is 28 out of 100 more than 20%?
Yes.
Yes, it is. Does that seem like we've got a speeding problem?
Yes.
Possibly. Because was that sampling variability, or do we have a true difference? That's why we do the full significance test. The null hypothesis is that we've got 20% speeding. The suspicion is that it's more than 20%, and therefore we need to get this camera, right, or the speed sensor. The resulting p-value is 0.023. What conclusion would we draw based on these significance levels? So the first one is alpha of 0.05. That is a significance level of 5%. That's basically our decision point. Anything above that, we did not get enough evidence. Anything below that, we've got really good evidence that the true proportion is more than 20%. So our p-value equals 0.023. And how is that related to this alpha? Is that less than or greater than?
Less than.
That is less than the alpha value of 0.05. And ladies and gentlemen,
Reject the whole.
we have a p-value that is low. So what do? We are going to reject this null hypothesis. Now, there's one last part of this. It is to say why, just to make sure we are clear, there is convincing evidence that P is greater than 20%. Notice, ladies and gentlemen, that I have concluded based on the alternative hypothesis. We got convincing evidence of the alternative because we were trying to prove the alternative, and we got the evidence we needed. So, since the p-value was lower than the threshold of evidence, we rejected the null hypothesis, and we can confidently say that we have convincing evidence that the true proportion of speeding on Lake Forest is more than 20%. What's going to happen in this situation? Are we going to get the speed cameras and the sensors on this?
Yeah.
Yeah, so Officer Trainum takes this data over to McKinney PD. Says, look, we have convincing evidence that the true proportion that are speeding on Lake Forest is more than 20%. Give me my speed cameras. Give me all the things that you've promised me to get. The people that are in the budget for McKinney PD take one look at it and go, we don't have this kind of money. So what we think we should do is we should change the threshold. Put it at 1%. Change the significance level. Now alpha is 1%. And now, what is true about the p-value of 0.023? It's greater than the alpha of 0.01, the threshold for rejecting. So now, can we still reject the null hypothesis? No, now we've got to fail to reject the null hypothesis. Does that mean that the true proportion is truly 20%?
No.
Not necessarily. We're not accepting that hoe. But what this does mean is that there is not convincing evidence that P is greater than 0.2. Again, that's the alternative. Maybe at this point we got some evidence, but it wasn't good enough to compare to this threshold and get the speed sensor and the cameras. And now they don't have to buy them because they changed the threshold. This happens all the time. And now we don't get our cameras and sensors. Sad, right? Aren't you sad? Yes, ma'am.
Does it matter that the one above you did greater than 20% and this one's 0.2?
What do you mean? It should have been the same. No, it's the same because both ones are 20% or 0.2. All right, cool. By the way, you guys know State Plan Do Conclude, right? State Plan Do Conclude starts next week. This is the conclusion part of a State Plan Do Conclude. So you now know how to do the state mostly and the conclude. There it is. All right, cool. Type 1 and Type 2 errors. I have a couple questions for you. Do you think that an innocent person has ever been wrongly accused and gone to jail?
No, it's never happened.
That happens. Do you think that a guilty person has ever been considered not guilty and let back into the world?
Yeah.
O.J. Simpson, right? No, I'm kidding. Yeah, it happens. But wait, why does that happen? If a guilty person is sitting there, why would the jury say that they're not guilty? Because the evidence wasn't convincing enough. It did not pass that threshold of convincing, right? That is exactly what we are doing in stats as well. Sometimes we screw up. It just is what it is. So we have two types of errors. We have a type 1 and a type 2. Those are Roman numerals, by the way. Type 1. This is when we reject the null hypothesis, but should not have. In that situation, we said the evidence was convincing, but the null hypothesis was actually true. Now, I know that sounds like I just said that we should have accepted the null hypothesis, but that's not true, okay? We don't accept a hoe, right? Okay. Think about a trial again. So, you are innocent until proven guilty, okay? The jury comes back and says that you're either guilty or not guilty based on the amount of evidence that they have. They never say that you are in fact innocent. But think about that person. In real life, that person either is innocent or guilty, right? But the jury doesn't get to say that they are innocent. They only get to say if they're guilty based on the evidence. But in real life, they really are either guilty or innocent, okay? Our null hypothesis is either true or not in real life, but we're just looking for evidence of an alternative. And we either get that evidence or we don't, okay? All right, that's a type 1. Type 2. Type 2. A type 2 error is when we fail, watch this, fail to reject the null hypothesis. Why did I write it like that? This is to help you remember which one of the errors can happen in which situation. We fail to reject the null hypothesis, but should have rejected. In this situation, we did not say that the person was guilty, but they really were. Okay? In this situation, we did not reject the null. I'm sorry, I said that backwards. In this situation, we did not reject the innocence, the null hypothesis, but we should have rejected the innocence. Okay? This situation, we said the evidence was not convincing enough but the alternative was actually true. Now, one thing to point out, you can only make a type 1 error when you have rejected the null hypothesis. It's literally the definition of a type 1 error. A type 1 error is when you have rejected the null hypothesis, but you shouldn't have. You can only make a type 2 error if you have failed to reject the null hypothesis. You cannot make a type 2 error when you have rejected the null hypothesis. It's part of the definition, okay? So that's why if you write it this way, fail to reject, that can remind you that that can only be a type 2 error. Cool, cool? Cool. All right. Let's look at some examples. Oh, actually, no. Here's a really cool little chart. In actuality, either the null hypothesis is true or the alternative is true. Again, the person sitting in the courtroom is either innocent or guilty, okay? But our decision, based on the evidence that we have, is that we're either going to reject the null hypothesis or we're going to fail to reject the null hypothesis. Is this giving y'all Punnett Square vibes?
Yes.
Yeah, I'm sorry. Okay, now we need to kind of think about what's happening here. If in all actuality the null hypothesis really is true and we reject it, what has happened here? What kind of error has happened? That's the type 1 error. Now, I have some breaking news for you. The probability that we make a type 1 error is equal to the significance level. So when we have a significance level of 5%, that means we have a 5% chance of rejecting the null hypothesis when we should not have done that. Okay? 5% is our main alpha that we use. All right, let's think about this for a second. We have rejected the null hypothesis in favor of the alternative. And the alternative is true. What has happened here?
Type 2.
Nope.
Type 1.
Nope.
You're right.
Very good. We have rejected the null hypothesis in favor of the true alternative. We have done a good job, folks. We have sent a guilty person to jail. Let's go. What if we fail to reject the null hypothesis? We do not reject it. And the null hypothesis is true. What have we done?
Type 2.
Nope.
No, you're right.
Ah, you did a good job. Again, this is when we say that the person is not guilty and they truly are innocent. We just let an innocent person go free. Good job. But what if we fail to reject the null hypothesis, but the alternative was what was true?
Type 2.
That's a type 2. In this situation, we said they weren't guilty, and they murdered the person. Sad, right? All right, this is where OJ lives. So, type 2 error goes right there. What questions do you guys have about that chart? That's just to help you put it all together.
Does the probability of type 2 equal anything?
Ah, I'm so glad you asked that, Lexi. Lexi said, does the probability of a type 2 equal anything? It sure does. Anybody want to guess what it equals? Nope.
Zero.
You would think it's 1 minus alpha, but it's not.
Alpha minus 1.
It's not alpha minus 1.
Zero.
It's not 0.
Infinity.
1.
It's not 1. It is
Alpha.
beta. So, do any of you know the Greek alphabet? What's the first letter of the Greek alphabet? So the probability of type 1 error is alpha. That's the first letter of the Greek alphabet. The probability of a type 2 error is beta.
Can my friends come in?
I'll be quiet.
The probability of a type 2 error is beta. Beta is the second letter of a Greek alphabet. Let's look at an example. All right, kids, back to the speeding example, okay? Officer Tranum wants to determine if it's worth the cost to install speed sensor and traffic camera at the entrance of McKinney Boyd High School. McKinney PD will get the cameras if we can prove that the true proportion is less. Okay, check this out. The significance level is 5%. Significance level is 5%. We need to describe a type 1 and a type 2 error and the consequence of each. Type 1, that is when we reject the null hypothesis, but should not have. Okay, what does that mean in context of this problem? That means that we said there is convincing evidence that P is greater than 0.2, but it really isn't. Oh no! Hayden, what happens here?
It's a hoe.
If we say that the true proportion is greater than 20% and we find convincing evidence of that, what's going to happen with the speed sensors? Are we going to get them?
Let me consult my notes.
If we say we have convincing evidence that P is greater than 0.2, do we get the speed sensors and the traffic cameras?
No.
No.
Yes. Yes, we do. Yes.
Ladies and gentlemen, listen.
Yes.
If we say that we have convincing evidence that P is greater than 0.2, do we get the speed sensor and traffic cameras?
Yes.
Yes, but
Let's go. Doesn't look good.
that was the wrong decision. So what's the consequence here? We get the speed sensors and traffic cameras, but did we need them?
No.
No, we didn't. So we have wasted McKinney PD money.
Good.
It's tragic. So the consequence is we get unneeded cameras and sensors. We have wasted money. This is not good. This is bad. By the way, what's the probability that that has happened?
20%.
Nope.
Alpha.
Alpha, which is 0.05. The probability that we have wasted McKinney PD money is 5%. Okay. Type 2. That is when we fail to reject the null hypothesis, but should have rejected. Okay, so what happens in this situation? In this situation, we said there is not convincing evidence that P is greater than 0.2. We say that there's not convincing evidence that we have a speeding problem, but there is a problem. And what's the consequence of this one? If we fail to reject the null hypothesis, are we going to get the speed cameras?
No.
Nope. We are not going to get the speed cameras. But are they needed?
Yeah. Yes.
Yes. So what's the consequence here?
undocumented speeding.
We don't get the speed cameras. We don't get the sensors. We have speeding continue. Freshmen are getting hit and killed every day. It's just terrible.
That's a little too real, Miss Lakey.
Isn't this a bad, bad, bad thing? Just saying. So,
I mean, it already happened, Miss Lakey.
the consequence is an unsafe environment. Was that? Should I maybe not have said that?
Oh, no, it's funny.
Okay. All right. All right. So here's my question to you: which one of these is worse? Is it worse that we waste the money and get unneeded sensors, or is it worse that we have possible death?
Death.
Obviously, that's worse, right? So we would want to minimize this chance of happening. Yes, ma'am. Consequence? The consequence of it happening? Consequence of it happening? Wait, where? Oh, convincing evidence. I'm sorry. That one is convincing evidence. All right, cool.
Wait.
All right, here we go.
My physics teacher last year. Sorry, I was in a waiting room for like an hour and a half. And I was just about to get in my phone.
No way.
All right.
No way.
The probability, I've already said this once, so we're just going to write it really fast. Here it is, kids, write it down. The probability of a type 1 error is equal to the significance level. You got it? Write it down, come on. The probability of a type 1 error is equal to the significance level. You got it?
Write it down.
What letter of the Greek alphabet is alpha? The first one, type 1 error. The probability of type 1 error is alpha. You see that? You see how that goes together? Okay, cool. Ahem. In the previous example, we were testing the following hypothesis where P is the true proportion of all cars to speed in the school zone. Suppose that the police commissioner decided to carry out his own test using a random sample of 250 cars and a significance level of alpha equals 0.1. What is the probability that the police commissioner makes a type 1 error? 10%, 0.1. Ladies and gentlemen, if you miss that on the test, probability of a type 1 error is equal to alpha, which is literally given to you in the problem. 10 or 10%. 0.10 or 10%. Those should be the kind of questions on the test that you get right no matter what. Right? Right.
You should put more than one of those points on.
Yeah, that was actually crazy though. Giving Patrick
Last questions.
instead of the shorts.
All right. Hayden, stop. Hayden.
Unsafe environment.
Very. The manager of a fast food restaurant wants to reduce the proportion of drive-through customers. Shh. 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 The manager of a fast food restaurant wants to reduce the proportion of drive-through customers who have to wait longer than 2 minutes to receive their food after placing an order. Based on store records, the proportion of customers who had to wait longer than 2 minutes was P equals 0.63. That's what is happening. That is the status quo. To reduce this proportion, the manager assigns an additional employee to the drive-through orders. During the next month, the manager collects a random sample of 250 drive-through times and finds that the new P hat is 0.576. Ladies and gentlemen, did the proportion of customers that had to wait longer than 2 minutes go down?
Yes.
Does it look like this person made a difference?
Yes.
But did they really, or was that sampling variability? Hence why we do the whole rest of the problem. All right, we have alpha, a significance level of 0.1. Our null hypothesis is that the true proportion continues to be the status quo. The alternative is that the true proportion is less than 63%, and therefore they did good. The p-value, the p-value is 0.0385. We need to interpret this. Assuming the true proportion has been 0.63, there is a 0.0385, basically a 3.85% chance that our sample is 0.576 or less due to sampling variability. Assuming that the true proportion has been 63%, there's basically a 4% chance that our sample was sampling variability. That means that there's basically a 96% chance. That means that there's basically a 96% chance that there was actual difference made. Okay? Now, the threshold for convincing evidence is 0.1 or 10%. So let's see. That's the last part. We'll get there in a second. Actually, we're going to just skip down and do that right now. Part C. This is part C. Everybody, we are on part C. We skipped part B for a second. Do you got me? The p-value is 0.0385. How does that relate to the threshold or the alpha that the manager has chosen? That is less than the alpha of 0.1. And what do we do when the p-value is low? We are going to reject this null hypothesis because there is convincing evidence that P is less than the 63%. Again, that is the alternative hypothesis. We have convincing evidence that this person has made a difference. Good for them. It was 63%, wasn't it? Okay. All right. Oh, but I don't know. Okay.
Literally, like, you can see a difference in numbers, so like, why do you have to do that?
Well, because sometimes it's not that obvious. That's why. All right, now back to part B, our errors here. A type 1 error. This is, we say, yeah, we say we have convincing evidence that P is less than 0.63, but it really is not. What's the consequence here? Gentlemen, what's the consequence here? If we say that the true proportion that have to wait longer than 2 minutes is less than 0.63, are we going to keep that new employee?
No.
If we say that the true proportion is less now, wouldn't we keep that person? Shows that they made a big difference, right? But it's really not lower. So they really didn't make a difference. So what are we going to do with this employee? Are we going to keep him?
Fired.
Yeah, we're going to keep this person, but we shouldn't. We should not have. We're going to keep an unnecessary employee. A type 2 error. This is, we say, we do not have convincing evidence that P is less than 0.63, but it really is. What's going to happen to that employee in this situation? Yeah, we're going to fire a good employee. And guess what? Our drive-through times are going to still be just as bad as they've always been, even though this person helped them make a difference.